I've got a short film for you just to get you into the right frame of mind. Shield wall, and off it goes. Organization. The assembly of individual units into one coherent functional system. Strength, not from numbers, but from repetitive regularity. That was the key to the success of the marauding Vikings or the all-conquering Roman legions. But it is also the secret to the success of a true megastar of chemistry, the polymer. Mass organization of molecules into long-chained, interlinked molecules of many, many thousands of units. Engendering properties of strength, resilience, and durability. My name is Dr. Michael Londesborough, and what I want to give to you today is a reflection on the main innovations that have pushed forward polymer chemistry. And I'm going to start with this. This simple, white, crystalline compound, perhaps the most important chemical we have on our planet. Sugar. The product of the remarkable genius of photosynthesis that takes carbon dioxide from the atmosphere, water from the ground, and converts it into this. A carbohydrate. Sugar is chemical potential. It's literally crystallized sunshine. It's the beginning point of all organic chemistry. And when a plant makes its sugar and it has an excess, what it does is it takes individual molecules of glucose and it begins to stick them together, to polymerize them from a monomer to a dimer to a trimer, and it'll keep on going to form a polymer, and that polymer we know as cellulose, the most abundant natural polymer that we have. And we make good use of cellulose. Could we have the animation, please? We make paper from it. But we also, here we are, here's the molecules of glucose linking together into polymer chains. These form microfibrils, which go into bigger fibers. And then we can eventually use these not just to make paper, but for example, a lovely dress. It was this natural polymer that about 200 years ago, a German-Swiss chemist called Schönbein decided to do a little bit of chemistry with it. Decided to play about with this natural polymer in his laboratory. And the result was this. Emma, could I ask you to come and help me, please? He found a way to take some cellulose, cotton, and he found a way in his lab how to saturate it with lots of nitrogen and oxygen. I'm going to give you some glasses as well, Emma, just to... I want to reserve your beauty.
Thank you so much.
Can you just hold that?
At least keep my sight.
Can you just hold that for me, please?
Sure.
No, just on the edge. That's it. Out in front of you. Thanks very much.
Yeah, still have a hand.
You still have a hand.
Yeah.
Well done. So, do you notice that? Maybe I'll repeat it just for... Thank you, Emma.
Are you sure?
Yes.
Yes. Do you want the glasses back?
No, you can keep on. They're
You're
yours.
Not going to need
They're
them.
for you. They're for
All
you,
right.
with love. So, our cellulose, once Schönbein realized that if he does some chemistry with it, he can form a new compound, a new material that is able to, well, has the property, as I've just demonstrated to you now, burn extremely quickly. And another thing I want you to notice, with almost no smoke. This combustion, with a smokeless combustion, is extremely important innovation in polymer chemistry. Because it was useful in an industry where they needed smokeless combustion, such, for example, in the armament industry, where you'd have cannons firing on ships. Imagine you've been on the deck of a ship, the English fighting the French. And inside the deck of all these cannons, the smoke in the room. This new natural polymer material resolved a problem. It set a precedent that through doing chemistry with these natural polymers, we can solve problems and they're lucrative. And we can do mass production that's economically viable. This is a very important aspect, that economic aspect of that. Then, we go a couple of decades later, we have our next innovative drive. And it surrounds the gentlemen's clubs of London, where they played billiards. Now, billiard balls then, this is 160 years ago, 140 years ago, they were made exclusively from ivory, from elephants' tusks. Therefore, they were very expensive, and if they were poorly made, they could be very delicate. But the main thing is that people began to realize that it was contributing to the endangerment of the valuable species of the elephant. They needed to find a replacement for the billiard ball. A replacement for the billiard ball. That was the inspiration which led then to the chemistry. A company put out an offer, $10,000, to the man or woman who comes up with a solution, how to replace the billiard ball. A new material was required. One innovative chap, a chemist, decided to go back into the work of Schoenbein with his nitrocellulose fibers, his polymer. And he started to do some more chemistry. And it led to a new form of this nitrocellulose, camphorized. You might know it as celluloid. Celluloid film, celluloid billiard balls. And he won the prize. The first thermoplastic, which means it's a polymer that you can, after you make it, you can heat it up, melt it down, and you can form it into any shape you wish, whether it be a billiard ball or a film or whatever material. So an innovation that came from a demand that was then that was the X prize of the day. $10,000 was equivalent to about $500,000 in today's money. A big X prize, somebody went for it, came to the solution. Of course, there was the problem that celluloid retains some of the highly flammable properties of nitrocellulose. So there were occasions where all of a sudden they're playing billiards in the gentleman's club and one of the balls would explode. But nevertheless, that set the ball rolling and again reconfirmed to people that work on polymers is financially viable and provides solutions. But it's not just sugar that nature polymerizes. Nature polymerizes other fundamental substances which it has. For example, amino acids. Okay? The building blocks of proteins. Every amino acid has on one side an amine group, that's a NH2 group, and on the other side a carboxylic acid group, COOH. They love each other. If another amino acid comes along, the amine group and the carboxylic group form a bond, we call a peptide link, and releases a molecule of water. This continues to form a polymer chain of amino acids or peptides, a polypeptide, which we call a protein. Your bodies are doing this synthesis now in you. One of the most famous examples that we use quite regularly is this: silk, a polypeptide, a polymer of amino acids made by the silkworm. And the result is a fabric that is one of the strongest we know, and yet very light because of the intermolecular linking between chains. Now, this beautiful piece of material is perfect for an evening gown for, let's say, you, Emma.
Yes.
But also, it's a perfect material for parachutes. Lightweight and strong. You can really fly on it in the wind. Now, during the Second World War, the demand for parachutes, for obvious reasons, was very high. But the silkworm is only indigenous to certain parts of the world. All of a sudden, there was an economic problem, an economic reason why to find a substitute for silk. We need lots of parachutes, and we need them now. We haven't got the silk. Figure it out. Chemists began to try and figure it out. Wallace Carruthers is an amazing chemist who you might have heard his name. And he began to look into this. He began to look into this particular problem. And of course, he realized that silk was a polypeptide, which means that they are, as I said, the amines and carboxylic acid groups linking together. Of course, you can't just go and buy or distill from crude oil amino acids. So he was thinking, what can I use? Are there other chemicals, easily attainable, cheap, that I can use and use this natural technology of peptide links to link them together? And he came up with the following. He had an amine, hexadiamine, which is, I've got this molecule here, freshly prepared in the lab. I've got a bit of food coloring, just so you can see it a bit better. Otherwise, it's colorless, of course. I've made it nice and red. I'm going to put it into my wine glass. So this is a double amine. What the molecule is, you've got those two amine groups, the NH2 at either end. And in the middle, there's a chain of 6 carbon atoms. And here is adipic acid, which is also has got a chain length of 6 carbon atoms. And at the end, at both ends, we have 2 carboxylic acid groups. Now, the acid is dissolved in an organic solvent, and the diamine was dissolved in water. So we can form 2 layers. Can you see that? I'm hoping you can see it on the screen. 2 clear layers. In the same way as oil floats on water, organic liquids also float on water. So there we have it. Now, as we speak, the polymerization is occurring. I don't know if the cameraman, can you get a close-up there? Can anybody come in with a close-up? You get right in towards there. You can just see here on the interface of the 2 layers, we now have the polymerization taking effect. Okay, so the amine groups are reacting with the carboxylic acid groups. They're beginning to form these peptide links, and we're beginning to form this polymer of 6 atoms of carbon, peptide link, 6 atoms of carbon, peptide link, 6 atoms of carbon, peptide link, and so on. Come and help, Emma.
That was a lovely choreography.
Thank you.
So I feel like the wizard's assistant now.
Okay, so
for the first time in my life.
Take some gloves. There you go. Put them on. I want to, again, maintain your health and safety.
That would be nice.
Maybe, have you got your glasses still?
No, I brought them away, so I'll just go pick them.
And what I want to do is I want to show you, imagine now you are Wallace Carruthers. You've been working a long time on this problem. You've been asked to go and find it out, work it out, find that solution. Take your influence, take your inspiration from nature, but make it cheaper. Imagine he's got this set up now, and this is the crucial moment, Emma. The polymerization is occurring at the interface layer of these two layers. Now watch this. I'm going to literally pick up these new molecules of polymer. With my tweezers, I'm going to go in. Here it is. This is our new polymer. Okay, Emma, what I'm going to do is I want you to really carefully take hold of that. Okay, and start pulling up, and then take your other hand and pull that up. Pull that up again. Right. Nice and soft. Oh, a bit too fast.
Too fast?
We'll do it again.
Sorry,
you can put it down on the table.
Okay.
Here we go. Look, I'll show you. This is what Carruthers saw. This, do you want to take over?
I do.
Is polymerization in action right before your very eyes. Emma, I want you to carry on. I want to show you, I want you to see just how much we can pull out of such a small volume of chemicals.
When does it end?
It ends once we can consume all the chemical compounds. Just enjoy that for a moment. Just let that sink into your head. Just allow that. Can you imagine being that person at that time, thinking, what have I done? What he had done was he'd come across the first synthetic polymer. This is no longer now a natural polymer which we've adjusted. This is the first synthetic polymer. Cheap, easily gettable starting materials, and we've got an amazing polymer material which we can just draw out. It's easy. But you know what else? Keep going, Emma. Keep going. You're looking good. This is nylon. What you're seeing here is the synthesis of nylon, the first synthetic polymer. This is nylon 6,6. You remember it's called 6,6 because there's 6 atoms of carbon between the linking groups. Carruthers also realized that this number of atoms, or the nature of the structure between the linking groups, is key to the properties of the polymer. So, okay, chaps, can we go back to the Emma, you keep going. They can see you. Can we go back to the presentation? And so he realized that if you have nylon 6,6, 6 atoms of carbon, 6 atoms of carbon, 6 atoms of carbon, the polymer you get is perfect for ladies' stockings. It's soft to the touch, nice and smooth. If you have 6 atoms of carbon, 10 atoms of carbon, 6 atoms of carbon, 10 atoms of carbon, you get a polymer which is harder and more robust. Perfect for toothbrush heads. Do you see what I'm getting at? You do a little bit of changing, and you get a new product. A whole new world of possibility opens up. You can begin to tailor your chemistry to products.
I think we're done.
We're done.
Yes.
She did a really good job. Please, can you give a little round of applause for Emma? Thank you, Emma. Thank you very much.
Thanks. Thanks for taking me in. It's fascinating.
Okay.
May I leave?
You may indeed. I'll call you in a bit when I need you next.
Great. I'll see you later.
So, let's develop this theme a bit. What happens if we, for example, we leave these aliphatic chains in nylon aside, and we put something else? Here we've got a polymer of styrene. Now, styrene doesn't have any chains. It's like a ring structure. It's an aromatic ring. Okay? And if you polymerize styrene, you get polystyrene, which I'm sure you've heard all about. Now, polystyrene is an almost ubiquitous polymer. You find it everywhere. It's got loads of good uses. One of the most important properties is that it's very good at encapsulating air. The resultant polymer being low density, very light and highly voluminous, which is the ideal material for insulatory materials that we can use at home, for example. Or to keep your Chinese takeaway warm when you're going home. Okay? Now, polystyrene is great as well because it's very durable. Okay? It can last for a long, long time. But on the other hand, that can be also a bad aspect to it. Because if it lasts for a long, long time, it stays in our environment for a long, long, long time. Hundreds, maybe thousands of years. This is one of the new problems coming from these new sets of materials. A new problem of what to do with this waste. which indeed our next speaker is going to be concentrating on. Fascinating work coming from there. But I'm going to show you a little chemist's trick, what we can do with this polystyrene waste. I have here, from my laboratory, the bottomless coffee cup. You've heard of the bottomless cup of coffee when you go to an American restaurant where you can keep on turning up and filling it further. Well, this is the chemist's version. Allow me to show you why it's bottomless. Okay. Oh. Oh. There we go, see? Without a bottom. It's very good at just making polystyrene literally disappear. You can see there's nothing underneath my... And if that's not enough for you, I can repeat the dose. It's not a problem at all. I'll take another one. So that's already 1 meter of polystyrene going in. Let's have another one. Now, this can go on and on and on for a long, long time. I can get rid of a lot of polystyrene in my bottomless cup. Rather impressive, isn't it? I could keep on going. I could maybe even do a little business about this, collecting polystyrene and making it disappear into my cup. You're welcome to buy it from me if you want it. Would you like me to drink it? Can I drink it? No, but I'm going to show you something even better I can do with it in a minute. But hold your horses. This is my friend. You can do all sorts of tricks with this. The production staff had a joke that this looks like me. It probably does. But I'll let you into the secret. My bottomless cup contained this liquid, which is called acetone. Acetone it's the same thing as ladies use to remove their nail varnish. And it's very good at dissolving polystyrene. And what happens is I'm basically breaking up these long polymer chains of the polystyrene, and I'm releasing its major component. Its major component, of course, as I said earlier, is air. So we're just getting rid of the air here from the head, and you can see the bubbles of air being removed, and what I'm left with is a solution of polystyrene. Now, this is not in itself. This is not, to go to the gentleman's question, this is not waste. A clever chemist can always do something with waste. What I can do is I can take this waste. If I can ask the cameraman please to step back a little bit so that the people can see. Můžu vás poprosit? I can take this waste, which is the solution of polystyrene, and I can add in some of the molecules of boron hydride that I so love, which I do in my own laboratory. Molecules that can do something rather impressive. They fluoresce. So if I can ask for the lights to go down, can the lights go down as much as possible? Okay. So I've got some of my molecules here. Okay. Now you can't see them at the moment. They're in a solution with the polystyrene. If I bring them, though, towards this UV lamp, you begin to see the difference. Okay? So in the presence and in the absence of an ultraviolet field, nothing. If we add in the ultraviolet field, we begin to get the property of fluorescence. Now, the important aspect is that it's caught up into the matrix of this polystyrene. That allows me to make new materials with this mixture. For example, I can show you here. This is also I made last week in my laboratory, where I've taken one of the same molecules of the blue fluorescent material, and you can see here, this is polystyrene. I've got a lovely, wonderful polystyrene, which otherwise would be colorless. Inside the UV, it gives a lovely blue emission. And I can create any sorts of objects with this. Indeed, I can even use other polymers which are semiconductive. So I can run an electric current through it and achieve fluorescence, emission of light, using this polymer matrix of my molecules. Indeed, we can do all sorts of interesting stuff, like this over here. This is another polymer. Keep the lights low. And I've got my molecules in it, and I can write you a message. Lights off. So this is a PVC polymer with my molecules implanted, and I can write some nice things for you all there. Or indeed, if I take a bigger, can I ask, Emma, can you come and help me, please?
Sure, just tell me how.
Just hold this up for me, please.
Wonderful.
So here we go. This is a PVC polymer. I've doped it with my compounds. I've got here a laser pen, and can you see where the energy impacts on our polymer layer? That excites the molecules. The molecules become excited. They go to an excited state. They fall back down. They release the light. We can do all sorts of interesting things. So this is one example of a possible reaction and action of our polymers. Thanks very much, Emma.
You're very welcome.
Okay, lights back on. I'm unfortunately coming to the end of my time, so I wanted to perhaps show you one last polymer I've got in my bag here. Again, fresh from the lab. This polymer has a wonderful property, which I'd like to demonstrate to you. In between the interlinking components, we have a compound that can do something really, truly remarkable. I only need a tiny amount of the polymer. Okay, that's enough. So this is my polymer. I'm going to show you what it can do, and then I want you to see if you can think about how we can use it. Here's my, oh, this is heavy. A lot of water. If I add the water in, all the way to the top, watch what happens. The water now is gone. It's no longer a liquid. It's solidified. If I take my bowl here, the water's gone. And yet such a small amount of the molecule. I'm going to show you one more time, okay? One more time. Let's get a bit more of my polymer into here. Okay, in it goes. Right. I'm going to get some water. You're watching carefully. Okay. I can keep pouring. I can keep pouring. I can keep pouring. I can keep pouring. This polymer is sodium polyacrylate. You got an idea where we use it? Where it makes money? This polymer revolutionized in the 1980s babies' diapers. Okay? It's got the possibility inside of you, open up one of these little babies, you'll find some cotton wool, and amongst the cotton wool, there'll be, there we go, those tiny little grains. That's your polymer. It can absorb up to 300 times more of its molecular weight in water. Where else can it be used? It's not just helping babies, keeping them dry. It's helping the astronauts of NASA with their economizing of water when they leave the planet. There's even rumors that the sheikhs of the Saudi Arabian peninsula are going to use this polymer to encapsulate water to enable golf courses in their deserts. The possibilities are almost endless for polymers. All it needs is you. Thank you very much. Thank you.